Good morning to all. Today I will be presenting about MSTID probabilistic forecasting and demonstrations, what we have done in this T-FORS project. This is the part of work package 3. Uh, just I want to give a small introduction about the work package 3, where we had two main objectives. First, to establish the climatology over the European sector, and then based on the observed result, the climatology develop a probabilistic forecasting uh, model or techniques for the MS studies over Europe. So we have played with many techniques, and we finally come up with this idea of quartile-based probabilistic forecasting method. So in order to do that, first we use the T-tender TEC, which is basically derived from the n number of GPS as well as GNSS receivers located over Europe to identify the MSTIDs. In general, what we do, we remove the 1 hour running mean from the original TEC value, and then this T-tender TEC will be in the slant, and it will be converted into the vertical TEC. So this method is efficient to identify the small perturbation. Let us say when compared to the LSTIDs, the TIDs may be having very few TEC, even 0.5 or 0.2 TEC unit perturbation. So first, we have to, before applying this method, whole Europe, we also have to have a better validation whether this method is working properly, whether we can use it. So what we did, we selected the location where the ionization is also there. That particular location, we estimate the T-tender TEC, estimated T-tender TEC, which is temporal resolution of 30 seconds, and for a whole year, and then we can estimate the first and second, third quartiles of the T-tender TECs. So for each month, so that will give the smooth variability with respect to time for each month, how much it is changing with respect to the time. So we used 4 stations like let us say Fairford and Prohonice to represent the high mid latitudes, because which is located nearly 50-degree north latitudes, and Rockets and San Vito for the lower mid latitudes, which is located around 40-degree north. So here you can see the T-tender TEC median values for Prohonice and Ibiros. The x-axis is the day of the year, and the y-axis is the time of the day. And you can see large variations, and also if you are looking the y-axis, you also can see the clear like a temporal variation, variation with respect to time. And also see the solar terminator effect, which is very clearly seen. And also we can see some seasonal dependency in this T-tender TEC variation. And overall, this is having kind of consistency with the MSTID climatology, what we have observed. And this is the same plot for other 2 stations, which is Prohonice and San Vito. You can see here. They look almost similar, and if you are seeing here, there is large variation between these 2 stations. One of the reason could be due to the lower elevation angle of the satellite, and other thing also could be due to the large regional dependency of this T-tender TEC variability. Of course, the MSTD also have large regional dependency. So This here I will be showing some of the example how good these quartile based probabilistic forecasting techniques. This is one of the example for the Hungatunga, the well-known Hungatunga eruption event on 15 January 2022. You see here the black and red lines represent the first and third quartile as well as the median for the whole month of January 2022, and the green lines represent the uh, January 15th T10 TEC. You can see large wave undulation. And what is the criteria we assume here? When the T10 TEC is exceeding above or below the first and third quartile consecutively, then if this can be an indication of the TIDs. So I'm not pronouncing here MSTID. It can be classified as a TIDs. And if the fluctuations are so frequent or very, let us say that periods are less than 1.5 hour, then we can expect those can be MSTIDs. The large scale, the large temporal scale can be MSTID, LSTIDs. So this technique can identify both. It's not only for the MSTIDs alone. But here, if you are looking, this is the time. Uh, this is for the four station, what I was telling, Jolisru, Perhonais, Sopron, and rockets here. And here you see there is a peak here in all these four stations. This is the time when the Hungatunga associated wave activity reached over the European sector. And we also cross-checked with the previous reports already published in our journals. And additionally, we also can see some other perturbation. This is that I will come to next slide. What are they? So we could see the Hungatunga event clearly. And additionally, we also see some other wave activities. To validate this, we use the kiogram for the large area over the European sector for the four station. Near to the four stations. Um, this is the latitudinal variation, the y-axis, and x-axis is the time for all these four plots. You can see that in the daytime there are some large scale TAD activities here, and the point of interest is this portion where you can see more small scale MSTIDs here. So this is the time. If you're going back, this is the time where we also the quartile based method also can show the um, MSTIDs activities clearly. And then we also checked other quiet time, like there is no much other geomagnetic activities or effect. Then how good this quartile based method to detecting the MSTIDs. Here you can see very clearly, right? If the time period is, if you're looking the peak to peak, the time period may be less than 30 minutes. So, and additionally, we also see the second recurrent signature of the Hungatunga eruption in the midnight. It was also well reported. And this is the daytime MSTIDs, which is very quite visible in the quartile based method. And how it looks in the kiyograms, yes, you can see here very nice daytime MSTID activities. Also, there are some signature of disturbances in the nighttime. So then we also looked for the geometric disturbed condition, how it is. This is for the case of 26 to 28 February 2022 geometric activity. Here I am only showing on 27th February 2020. Sorry, it is 2023. Here you can see large fluctuations, but they are mostly related to the LSTIDs here. And also this is another event for March 2023. This is also associated with the LSTIDs. And this is the quiet time. You can see the perturbations are not falling within the category of our classification. So now this is one of the tropospheric, severe tropospheric event, which we carried out a special study on this event. I mean, we looked at many strong tropospheric weather activity events, and we selected a couple of events to look more detail to identify the potential indicator for the MSTIDs. So here we have looked for 4 consecutive days where the severe tropospheric weather event was located, observed over the European sector. And here you can see this is the whole August month, first and third quartiles in the red and black color, and the blue and green indicate the particular day T-tender TC variability. You can see large variability here. This could be a MSTID signature, but when we try to check those things in the QGram, of course, the QGram does not show any clear feature in the of MSTID. However, in the particular location, we can see large fluctuation of MSTID activity. And this is other 2 days, 28 and 29. Also, we can see large variations. And here, one point I want to mention, I want to stress here is that if you are looking the QGram, in the QGram, we are not seeing such a very clear signature in all the day. But in the T-tender-TC at a particular location, we see large fluctuations, and which is always almost exceeding the quartile values. But here, what is important is like if you are looking the QGram, there are some particular locations. You can see a large MSTD activities, the nighttime MSTD activity here and here. So the MSTDs are very, very regional specific. They exist very narrow region, let us say 5-degree latitude and 5-degree longitude. So it is it is not possible to provide any reasonable forecasting for whole region. Let us say whole Europe is maybe having large false uh, probabilities. Instead of that, if we specifically focus on locations, let us say one sound and related to like less than 1,000 kilometer or 1,500 kilometer regional one for forecast, that would be more efficient to give the reasonable forecasting for MSTIDs, because they are really very regional specific. Even though if you are seeing the climatology or the seasonal variability all over the places, they may look similar, like winter maximum daytime MSTID activities, summer maximum nighttime MSTID activities. That is good. But when we try to see this kind of forecasting, then it is very difficult. Their occurrence intensity or occurrence locations are really have large variabilities. So this event we also checked with the ionosonde observation, and you can see for what I was talking here. You can see there are all these ionosondes are located over the European region. There are 7 ionosondes you can see. The color bar in the background shows the intensity of the MSTD activities. You see, they are not uniform, right? You can see some stations and some days are very strong, and some days are the same days at other station it is not that strong. So they have large regional dependent. So using this forecasting method, what our idea is like at least take more number of days, at least 30 days of TEC map, and estimate the quartiles, and when the current time, let us say the now cost kind of. So when the TEC is exceeding above the quartile, the first and third quartile, then we can provide an alert for the presence of MSTIDs. And also, sometimes there is another problem here is that when we generally use this quartile, the first and third quartile criteria, in this category, as I showed a couple of examples, LSTD also will fall. So then we also have to fix the time frame and the duration, which we have to do more studies to fix properly what is the potential time, duration, and to avoid the LSTD contamination if you only focus on MSTD probability forecasting. Yeah, thank you very much for your attention.